Hello everyone, welcome back to the MP Coding Linux Device Driver Development tutorial series. Today we are going to understand the device tree. When we talk about embedded Linux systems or custom SoC, we need to know about the device tree because that's where we describe the hardware, peripherals, clocks, and so on. So the device tree is the starting point for a custom embedded Linux systems. Now, some RTOSes also use the device tree. For example, the Zephyr project also uses the device tree to configure the hardware of the system. Okay, let's understand this. The device tree is a data structure used by the Linux kernel to describe hardware that cannot be automatically discovered, such as peripherals on embedded platforms like RaspberryPi, NXP, RAXA, and so on. Instead of hard-coding board-specific hardware details into the kernel source, the device tree externalizes this information into a human-readable text format, the .dts file, which is then compiled into a binary blob, the .dtb file, and passed to the kernel at boot time. This 2006 paper by IBM advocated for a standard method of describing hardware to the Linux kernel. Because of this, the device tree became the de facto standard for telling the Linux kernel what hardware is present on the board and how to configure it at boot time. If you head to devicetree.org, you can see the official specification for the device tree. Go to the specifications section and open the latest release. I will go to version 0.4, which takes us to the GitHub page where we can download the PDF version of the device tree specification. Let's open that PDF. If we go to section 2.2, we get a diagram that gives us an example of a device tree structure. The device tree is a data structure used to describe what drivers should be used for what hardware, along with the associated settings, just like a JSON document. While it is essentially just a text document, it creates this kind of tree structure where each node can contain one or more properties and one or more subnodes, also called child nodes. For example, here we can see, these are properties. And these are also properties. And also can be contain one or more subnodes or child nodes. You can see this as the root node is given by /, and it has some properties of its own, as well as several subnodes. For instance, the CPU's node, it has two own properties, with two child nodes, CPU0 and CPU1. And each of those also has properties associated with it. A node can only have one parent, and that is what creates this tree-like structure. If we go down to section 2.2.3, it talks about path names. And this is how you can address nodes along a path in the device tree. It always starts from the root node. Think of it like Linux file system. So, start with a / for the root, then the node name, then another /, and then the next node name, which is a child of the first one. You can see an example here with the CPUs and CPU1 nodes from figure 2.1. So if we go back to figure 2.1, following this path structure, it would be /CPUs /CPU0 if you want to address that specific node. And from there, you can also access the individual properties inside that node. If we go to the section 2.3 Standard Properties, here we can see some standard properties. The whole section 2.3 covers these reserved property names, and they each have a specific meaning to the device tree compiler, also known as dtsi. The compatible property is a special keyword used to find what are known as bindings. Bindings are files such as source code, configuration settings, and so on that define how device tree data should be interpreted by the software. For example, using the compatible property, you can tell the operating system where to locate the appropriate device driver. In this case, it would try to locate a device driver matching the name FSL MPC8641, where FSL is typically the manufacturer name, which here stands for Freescale, and MPC8641 is the specific device name. You can list multiple compatible strings separated by commas. It would try to match the first one, and if it couldn't find a driver for that, it would fall back and try the next one. In this case, INS16550. This fallback mechanism allows drivers to support both specific and generic hardware variants. The model property is also a reserved keyword that provides more information about the device, specifically the manufacturer and model number of the device. Next, we can see the phandle property. The phandle property specifies a numerical identifier for a node that is unique within the device tree. An important thing to note here is phandles are automatically assigned by the device tree compiler. So when you create a node and run the device tree compiler, you can inspect the compiled output and you will see phandles being assigned automatically. This means you should not be manually assigning the phandle property yourself. Just let the device tree compiler handle that for you. Another property you will see a lot is status. This simply describes the operational status of a device, and there are several possible values. Note that these are string values. OK means that the device is operational. In other words, it tells the kernel to enable and probe the driver for this device. Disabled means the device is not currently operational, so the kernel will not probe the driver for it. There are other status values as well, but in practice, OK and disabled are by far the most common ones you will encounter in Linux device trees. Next, you will also come across hash address cells and hash size cells. These are used to configure how child nodes under a given parent node describe their addresses and sizes. Think of them as defining the number of elements you need to pass to describe a child node's location and size. Note that the pound sign here does not have any special meaning. It is just part of the property name string, and it is a reserved keyword in the device tree specification. Hash address cells defines how many 32-bit values, or cells, are used to represent an address. Similarly, hash size cells defines how many cells are used to represent a size. So in this example, address cells is set to 1, and size cells is also set to 1, meaning a 32-bit value for the address and a 32-bit value for the size. These properties apply to the child nodes of the parent node they are defined in, and you will most commonly see them used in conjunction with the reg property. We will see exactly how this works in practice when we examine the Raspberry Pi device tree in a moment. The reg property is used to specify the memory-mapped register address, or bus address, of an associated device. We will see this in action when we start working with GPIO nodes, as well as bus-connected devices like I2C sensors. I already showed some examples of this in the Linux I2C subsystem example. If you did not watch that example, please go and watch that video. There, I have explained some properties of the device tree, so you will be familiar with the concept. If you are designing a custom embedded Linux system, you will need to correctly describe and configure your hardware using the device tree, and this document is very well documented. So please refer to it whenever you want to learn more about a specific node or keyword. Now, if we go back to section 2.2 and look at that figure we saw earlier, hopefully a few of these properties are starting to make more sense. For example, the compatible property lists the device driver we want to use, and the Linux build system will find the associated drivers for this. You will also see various property value types used throughout the device tree. Strings are defined with quotes. Integers are defined as plain numbers inside angle brackets. Hexadecimal integers are prefixed with 0x. And arrays are defined inside angle brackets with values separated by spaces. There are a few other types as well that we will see in a moment. What is important to understand is that this collection of nodes, subnodes, and properties allows us to configure our hardware devices in an abstract manner that is completely separate from our source code. Now, before we go further, let me quickly explain kconfig. When you build the Linux kernel, you need to decide which features and drivers to include in the build. Kconfig is the configuration system that lets you do that. On the Raspberry Pi, the kernel configuration that was used to build the currently running kernel is stored in a compressed file at /proc/config.gz. We can extract it like this. Now let's open it. And let's search for something familiar, like I2C. Here, Y means the feature is compiled directly into the kernel. M means it is compiled as a loadable kernel module, just like the modules we have been writing throughout this series. And if a line is commented out like this one, it means that feature is disabled and not included in the build at all. So think of kconfig as a way of configuring the software side of the kernel build, deciding what gets compiled in and what does not. The device tree, on the other hand, is used for configuring hardware elements, things physically connected to our processor, or in this case, our board. So why should we care about the device tree? Can't we just use kconfig? The reality is that kconfig only controls what gets compiled into the kernel. It does not describe what hardware is actually present on the board. The device tree fills that gap. It allows developers to write application code and drivers that are decoupled from each other and from the underlying hardware. It provides the glue that connects these layers together, and if used correctly, you can write device drivers that work across different hardware platforms. It also helps you map pins to peripherals and keeps your application code free of any hardware-specific configuration details. Now, keep in mind that in this tutorial series, we are not going to build the kernel from scratch. Our focus here is on understanding the device tree and device tree overlays, which are what we actually need for device driver development. So I will not be going too deep into kconfig. I just wanted to give you a basic understanding of what it is and how it relates to the bigger picture. Now we know what a device tree is. It is used to describe hardware. But why did the device tree concept come into play in the first place? On x86 PCs, hardware can be discovered dynamically via buses like PCI and USB. The operating system interrogates the bus and the devices identify themselves automatically. But on embedded platforms like ARM and RISC-V, peripherals are typically memory mapped and have no self-description mechanism. So historically, Linux handled this with what are called board support files, C-source files that hard-coded every platform's hardware layout directly into the kernel. This is an example for old way of hard-coded board file. This led to thousands of board-specific files being merged into the kernel source tree, which became a serious maintenance nightmare. The solution was the device tree. The concept was actually borrowed from open firmware, which was used in SunSpark and PowerPC systems, and it provides a standardized, platform-independent way to describe hardware in a tree-structured text file. With the device tree in place, the kernel no longer needs board-specific C code to describe hardware layout. The same kernel image can boot on multiple different boards, each with its own .dtb file. The hardware description is maintained completely outside the kernel source tree, and the bootloader is responsible for passing the .dtb file to the kernel at boot time. For example, on the Raspberry Pi, the bootloader loads the appropriate .dtb file for the board and passes its address to the kernel. The boot sequence looks like this. Bootloader loads kernel image and .dtb file. Then kernel parses the .dtb. And finally, drivers probe devices. Okay, now let's understand the device tree structure using the Raspberry Pi device tree as our example. In the Linux device tree, we come across multiple file types. As we discussed earlier, the .dts file is the device tree source. This is the human-readable, top-level board file that describes a specific board. The .dtsi file is the device tree source include. These are reusable fragments that contain SOC-level definitions and common platform settings that can be shared across multiple board files. The .dtb file is the device tree blob. This is the compiled binary version of the device tree that gets passed to the kernel at boot time. And the .dtbo file is the device tree blob overlay. This is a loadable overlay that allows you to modify or extend the device tree at runtime without having to recompile the entire device tree from scratch. We will be working a lot with overlays as we get deeper into device driver development. If we open the Raspberry Pi OS GitHub repository and navigate inside the directory arch/arm/boot/dts/broadcom, we can see the device tree source files, both .dts and .dtsi files, for the various Broadcom chips used across Raspberry Pi boards. Here we can find the .dts files that belong to each specific Raspberry Pi board. If we look at the BCM2711, for example, which is the SoC used on the Raspberry Pi 4 Model B, we can find several .dts and .dtsi files. These are the ones that get compiled into .dtb files and loaded by the bootloader at boot time. In the top-level DTS folder that contains additional device tree source files that come with the Raspberry Pi OS. Depending on which SoC and board variant you are running, the appropriate compiled .dtb file is selected and loaded into the kernel. Now let me show you this on the Raspberry Pi itself. If we look at the boot directory, we can see the compiled device tree blobs. These tell the operating system kernel exactly what hardware components are on the Raspberry Pi 4. And if we look inside the overlays directory, we can see all the device tree blob overlay files. These are the device tree overlays that can be selectively loaded at boot time, depending on what additional hardware or interfaces you have enabled on your Raspberry Pi. Now let's open the currently running kernel device tree. When our Raspberry Pi boots up, the kernel parses the flattened device tree, or FDT, that was passed to it by the bootloader. The kernel then extracts that data and builds a live virtual file system that you can browse at /sys/firmware/devicetree/base. If we look inside the base directory, we can see several properties that we already came across in the device tree specification PDF, things like compatible, model, hash address cells, and hash size cells. Now if we read the compatible property, we get back Raspberry Pi 4 Model B, BRCM, BCM2711. This tells the kernel exactly what board and SoC combination is present. The first string identifies the specific board, the Raspberry Pi 4 Model B, and the second string identifies the underlying SoC, which is the Broadcom BCM2711. This is how the kernel knows which drivers and configurations are compatible with this hardware. And we can also read the model property. This gives us a human-readable description of the board, Raspberry Pi 4 Model B Rev 1.4. This is exactly the model property we saw in the device tree specification. It simply gives more detailed information about the specific board revision. Now let's decompile the device tree into a human-readable .dts format. I have already explained how this is done in our I2C submodule example, and I have also added the commands here as well. First, if you haven't already installed the device tree compiler, you can install it using this command. And then you can decompile the currently running live device tree file system into a human-readable .dts file using this command. Here, -i fs tells the compiler that the input is a live device tree file system, the one the kernel has already parsed and mounted at /sys/firmware/devicetree/base. -o dts tells it to output human-readable device tree source format, and we redirect the output into a file called RPI for b.dts. This approach is actually more useful than decompiling a .dtb file directly, because it gives you the exact device tree that the kernel is currently using, including any overlays that were applied at boot time. I have already run this command and decompiled the file. Let me open it now. Now here at the top of the file, we can see some familiar properties: address cells, size cells, compatible, model, and so on. These are exactly what we saw when we browsed the terminal earlier. You will also notice there are lots of other properties and settings that we haven't discussed yet, but you can always look those up in the device tree specification PDF or by searching online. I am not going to go through each and every one of them here, but let's understand some of the important ones. So the file starts from the root node, represented by the /, and this is the root of the entire tree. All other nodes are children of this root node. Here in the root node, we can see hash address cells is set to 2, and hash size cells is set to 1. These values define how child nodes under the root should encode their reg property. Now let's look at a child node to understand how this actually works. If we open this CPU's node, we can see that it redefines its own hash address cells and hash size cells values. This means these new values now apply to the children of the CPU's node. And notice that the CPU's node itself does not have a reg property, so the parent's address cells and size cells values do not apply here. So let's look at another node where reg is actually used. The memory node is a good example. We can see here reg property used, and this is child of the root node, so root node's values applied here. Here, because the root node defined address cells as 2 and size cells as 1. The reg property is interpreted as 2 cells for the address and 1 cell for the size. And since there are multiple sets of values here, this is actually an array of memory regions, each entry describing a different region of physical memory available on the Raspberry Pi 4. Let me break this down simply. The node name is memory at 0, where the at 0 means this memory region starts at address 0. Remember, the root node defined address cells as 2 and size cells as 1. So every entry in this reg property is read as 2 cells for the address and 1 cell for the size. So this breaks down into 2 memory regions. First region, address 0x00 and 0x00, which combines to this one address. So it's starting at address 0. And size is this value. And it's actually 948 megabytes. And second region, these 2 addresses, which combines to this one address, starting at 1 gigabyte. And the size is this value, and which is about 3 gigabytes. So together, these 2 regions describe the full RAM available on the Raspberry Pi 4. The reason it is split into 2 regions is because the memory map has a gap in the middle that is reserved for memory map peripherals and other system resources. So the RAM is described as 2 separate contiguous blocks rather than 1 single block. Now let's go back to the CPU's node. Here we can see 4 CPU child nodes, CPU 0, CPU 1, CPU 2, and CPU 3, and 1 L2 cache 0 node. If we open the CPU 0 node, we can see some properties. At the top, we can see the compatible property, and it tells us this is an ARM Cortex-A72, which is the CPU core used inside the BCM2711 SoC on the Raspberry Pi 4. And since the BCM2711 is a quad-core processor, we have 4 individual processing cores described here, CPU 0, 1, 2, and 3. Each of these nodes represents 1 physical CPU core, and they each have their own set of properties describing things like clock speeds and power management settings. We can see those settings are set up here in the device tree. And alongside the CPU cores, we also have the L2 cache 0 node, which describes the level 2 cache memory that is shared across all 4 cores. Now let's take a look at the SoC node. The SoC node, which stands for System on Chip, is one of the most important nodes in the entire device tree. This is where all the on-chip peripherals and hardware blocks of the BCM2711 are described. If we open the SoC node, the first thing to notice is that it defines its own address cells and size cells, and it also has a ranges property. The ranges property here is important. It defines the address translation between the SoC's internal bus addresses and the CPU's physical addresses. This is because on the Raspberry Pi 4, The peripherals are accessed by the CPU at different addresses than what the SoC hardware internally uses. Inside the SoC node, you will find a large number of child nodes, each representing a different hardware peripheral on the chip. For example, DMA controller, GPIO, HDMI, I2C, interrupt controller, mailbox, MMC, pixel valve, power, PWM, serial, SPI, so on. Each of these child nodes has its own compatible property. NREG property describing its memory-mapped register address, interrupt lines, clock sources, and any other configuration needed for the kernel to initialize and drive that peripheral. This is essentially the hardware map of everything available on the BCM2711 SoC. And as we develop device drivers in the upcoming tutorials, we will be coming back to this SoC node frequently to understand how our drivers interact with the hardware. Now let's look at some familiar peripherals inside the SoC node. Let's take SPI as an example. I have already explained in detail how the SPI driver loads into the kernel using the device tree in the SPI subsystem video in this series. If you want to go deep into the driver source code and the SPI subsystem internals, please go and watch that video. But here, let's revisit it briefly from the device tree perspective, so we can clearly understand how the device tree drives the whole process of loading a peripheral driver into the kernel. So let's see how the SPI driver gets loaded into the kernel with the help of the device tree. Here we can see different SPI nodes, each with a different starting address. These represent all the SPI controllers available in the BCM2711 SoC that can potentially be used on this board. If we look inside the first SPI node, we can see its status property is set to OK, which means it is enabled and the kernel will probe its driver. But if we look at the other SPI nodes, we can see they are set to disabled, meaning those SPI buses are not currently in use. Now, if we want to enable one of these disabled SPI buses, we can write a device tree overlay that rewrites the status property to OK, along with any other required settings. I will show exactly how this is done when we work with our custom drivers in the upcoming tutorials. Okay, now let's head back to the first SPI node that has status set to OK. Here we can see that the clocks, CSGPIOS, interrupts, and reg properties are all configured. The reg property tells us the memory-mapped base address of this SPI controller and the size of its register space. Now look at the compatible property. Compatible equals BRCM, BCM2835 SPI. This is the key. This compatible string is exactly how the kernel knows which driver should handle this hardware. If we go to the RaspberryPi kernel GitHub repository and navigate to drivers/SPI directory and open the SPI BCM2835.c driver file, inside you will find something like this. Notice the exact same compatible string we saw in the device tree. This table is registered using module_device_table, which tells the kernel if a device tree node contains compatible equals BRCM, BCM2835 SPI, then this driver supports that hardware. So during boot, the process works like this. The kernel parses the device tree and finds the SPI controller node. It reads the compatible string and searches for a driver with a matching of _device_ID table. It finds BCM2835 SPI, and then the driver's probe function is called. At that point, the SPI controller is fully initialized and ready to use. We never manually inserted any module. The device tree and the driver matching mechanism handle everything automatically. Now if we go back to the device tree file, inside this SPI node we can also see two child nodes, SPI dev at 0 and SPI dev at 1. These represent the SPI devices connected to this controller. You will commonly see child nodes like these in RaspberryPi device tree overlays. This is exactly why in the /dev directory you see device files named SPI dev 0.0 and SPI dev 0.1. Here the first number is the SPI controller number, and the second number is the chip select line. And if you remember, when we enable SPI using RaspberryPi config, what it actually does is modify the /boot/firmware/config.txt file to add a device tree parameter. So, here this SPI equals to on means we have enabled the SPI driver. This instructs the RaspberryPi firmware to load the appropriate device tree overlay at boot time, which sets the status property of the SPI node to OK. And as we just saw, once that status is set to OK, the kernel finds the matching driver through the compatible string, calls its probe function, and the SPI interface becomes fully active. So RaspberryPi config is essentially just a user-friendly way of managing these device tree parameters for you behind the scenes. Now we know how useful the device tree is for configuring the hardware of a system. With the help of the device tree, we don't need to recompile the whole kernel just to add a new hardware driver. And we can also use the same kernel image for different SoCs. We just need to define the correct device trees and overlays for each board. I will not go into explaining each and every device tree property here, as there are a large number of them. You can always look up what they mean by searching online or referring to the device tree specification PDF. Some of the properties we will touch on in the next episodes when we write our own custom device tree overlays. Let me show you a real example. I have written a device tree overlay for the MAX72xx series chip, which is used to drive a 8x8 LED matrix display. Here, inside the source folder, in the DTS folder, I have created the MAX72xx overlay.dts file. Let me walk you through what is in here. At the very top, we have the standard dtsv1 and plugin. These are declarations. The plugin keyword tells the device tree compiler that this is an overlay, not a standalone device tree source file. Then we have compatible property in the root node. I have set it to BRCM BCM2835. This tells the bootloader that this overlay is intended for Broadcom BCM2835 based boards, which covers the Raspberry Pi family. Next, we have fragment at 0, which targets the root path of the running device tree. Inside the overlay block is where our actual device node is defined, MAX72xx_device. Looking at the properties inside this node, the compatible property is set to MAX72xx LED_matrix. This is the string our kernel driver will match against to bind to this device. The status is set to OK, which enables the device. The number_chips property tells the driver how many MAX72xx chips are chained on each row. In this case, 4 chips, giving us 32 pixel columns. For the GPIO lines, we have D in GPIOS, pointing to GPIO5 for the data line, CLK GPIOS, pointing to GPIO6 for the clock line, CSGPIOS, defining 3 chip select lines on GPIO 13, 24, and 25, 1 for each row of the matrix. Notice that the CSGPIO flags are set to 1, which means GPIO_active_low. This is because chip select lines are typically active low. The chip is selected when the pin is driven low. By declaring this in the device tree, the kernel's GPIO descriptor layer handles the polarity inversion automatically, so in the driver code we don't need to worry about it. We also have brightness and scroll delay properties that set the default display brightness and scrolling speed. And finally, at the bottom, we have the overrides block. This is a very useful feature of device tree overlays. It allows you to override specific properties at boot time directly from the /boot/firmware/config.txt file, like this. So without modifying or recompiling the overlay, you can tune these parameters just by editing a single line in config.txt. This is exactly the kind of flexibility that makes the device tree so powerful for embedded Linux development. Now we have the overlay file ready. Let's look at the module source file and see how these device tree settings are actually used inside the driver. Here in the source folder, we have MAX72xx driver. This is the main kernel module file. Let's open it. If we scroll down to where the device ID table is defined, you can see this. In the of_device_ID table, I have added the exact same compatible string that we defined in the device tree overlay file. So when the kernel parses the device tree at boot time and finds our MAX72xx_device node, it matches this compatible string, finds this driver, and calls its probe function. Now if I show you the probe function, you can see that the device tree properties are read directly inside it. We use of_property_read_u32 to read integer values like number_chips, brightness, and scroll delay. We use dvm_gpiod_get to get individual GPIO descriptors like dn and clk. And we use gpiod_count to find out how many chip select GPIOs are defined in the CS GPIOs array. This is how the driver reads its entire configuration from the device tree. No hard-coded values, no board-specific code. Now, in this video, I am not going to go into the full details of this driver. Later in the series, I will show you step-by-step how to develop this kind of custom driver together with a device tree overlay from scratch. So in today's video, we looked at an overview of the device tree, what it is, why it exists, how it is structured, how the compatible string drives driver matching, and how overlays are used to extend the running device tree. In the next video, we will write our very first device tree overlay example. We will cover how to write and compile a device tree overlay file and how to load it into the currently running device tree on the Raspberry Pi. So stay tuned, and if you enjoyed this video, please give it a like, share it, and subscribe to the channel. See you in the next video.